If you've spent any time on the SAT math section, you have likely stared down a problem exactly like this, a multi-layered fraction that seems designed to drain your time. Question instantly. We'll start with three terms. This is a constant, a number without a variable. This is a linear term, an expression where the variable x has no visible exponent. And this is a quadratic term, where the highest power on the variable is 2, like x squared. Categorizing the different pieces of an equation into these three groups allows you to see the underlying structure of a problem before you begin calculating. Step 1 is identifying the specific layout of our original expression. This problem features a constant in the main numerator and two nested fractions making up the main denominator. Step 2 is building a common denominator by looking at the bottom of those two nested fractions. We find the common denominator by taking the denominators from every term in the expression and multiplying them together. It is important to keep this expression grouped for now. Do not use the FOIL method on it yet. Establishing this exact common denominator is what allows us to eliminate the nested fractions in the next step. In step 3, we multiply the top and the bottom of our main fraction by that new common denominator. You must apply this to both the numerator and denominator, otherwise you change the actual value of the expression. Because any expression divided by itself equals 1, this whole action is mathematically identical to multiplying by 1. Step 4 is distributing that common denominator across both fractions in the bottom of the equation. This distribution causes the matching terms in the top and bottom of the nested fractions to cancel each other out. By canceling those terms, we have converted the multi-layered expression into a standard algebraic fraction. Now that the nested fractions are gone, the equation is in a much simpler state. Step 5 is finishing the algebra. We FOIL the numerator, multiplying those two binomials to get the quadratic expression x squared plus x minus 12. Then we add the like terms in the denominator, which gives us the linear expression 2x plus 1. Using these 5 steps, we've reduced 3 separate fractions into a single standard expression. This is our final result. But notice the mathematical relationship between where we started and where we ended. In the numerator, we multiplied a constant by 2 linear terms, which will always create a quadratic. In the denominator, we added 2 linear terms together, which will always create another linear expression. Because this mathematical path is consistent, whenever you see a constant over 2 linear fractions, the answer must be a quadratic expression over a linear expression. You can use that pattern to identify the correct choice by looking at the format of the options. Identifying these structural patterns helps you save valuable time for the math questions that require more detailed work. Try this 5-step method on 3 practice problems today to make the sequence second nature. Understanding how these equations are assembled changes how you approach the entire math section. If you want to see this applied to other topics, you can join our next live Q&A through the Discord link below.